Welcome to Secure Software Development. Let's just jump right into it. You've all seen these. These are magnetic door locks. They work by passing a small electrical current through an electromagnet. There's a strike plate. The electromagnet and the strike plate bond to each other, and you've got a pretty secure door. And it can also serve as intrusion detection, right? Because you can pass a small current actually through the strike plate, and that tells you whether the magnet and the strike plate are in contact or not. And you can use that to detect intrusions. So you've got a lock and you've got intrusion detection, and you also have a nice way of getting out if power fails, right? So one of the challenges with badged systems that lock the door is that if power fails, how do you get out? Right? You can't badge your way out. So you need a crash bar or something else like that in order to get out. Well, with these, power fails and you walk right out. So there you go. What you're looking at here is one very similar to one that's on our building at the lab. The one on our building is a grade 1 electromagnetic lock. I went ahead and looked it up, and it looks like it has 1,650 pounds of braking force. So if you can yank on the door with 1,650 pounds of force normal to the magnet, yank, you can open that door up. That's pretty secure. How would you get around something like this? Well, one way would be to kill power to the building. You kill power to the building, magnets off, and you can go on in. Killing power to a building is fairly challenging. It's fairly hard, right? Buildings draw a lot of power, and you can't just flip a switch and have that power change. Power, you can think of power having mass, or you could think of it as a giant flow of water. You can't just suddenly divert it, right? It's got inertia. And swinging a load like that is non-trivial, and things are going to happen, and people are going to notice, and it's going to be fairly hard. So maybe there's some easier way to get in. Let's think about the magnet itself. One way to get in, if you're a firefighter, is to get a halogen bar and just wedge it in there and use the principle of moments. Use some leverage to get in there. There's I'm guessing about a 4-inch tying up here and a 30-inch arm. So you need to apply 1,650 pounds of normal force right here at the end of this 4-inch arm. Here's your pivot, your fulcrum. And so you would take 1,650 and multiply it by the 4 inches to figure out the inch pounds that you need in this. And then you divide that by the 30 along here. And I don't know, you wind up with something like 220, I think, pounds you have to apply here at the end of the arm. So you apply that normal force down here and pop the door. That's very doable. You can do that. And for $267, you can pop your way into these buildings. Of course, if you're walking around with a halogen bar, prying the door open, it's likely people are going to notice, right? You may be on camera, people are going to see you doing that, and they'll think, well, that's not how you get into the building, and may report you, and there could be other problems as well. So something you should take that into account. But still, that's one way in. No one's watching and you want to get in the building, that's one way to do it. Well, maybe there are better ways. Let's think about the lock itself. So we know that magnetic force falls off with the cube of the distance. In reality, it falls off with the inverse square law, like everything else, right? You think about the area of the sphere as you move out, and that's the square of the distance. But magnets have positive and negative poles. Those cancel, and when you do the math, it winds up being about the inverse of the cube of the distance. But it depends a little bit on the geometry of it as well, right? You think about the poles and where they are in relation to where you are, and that can have an influence as well. So geometry, lots of other stuff goes into this, but if you take the time to actually do some measurements, you can wind up with a pretty curve like the one we have here, which we had to fit, but there it is. And with a little work and a little research, you can find these out for different kinds of locks, and this is one for a door lock that I looked up. And as you can see, as the distance increases, the force drops off fairly precipitously. Right, we start up here at 1,650 pounds in the ideal case, and then we drop. And out here we're down to, we're down in the, couple pounds range. Right, basically the door is open. So this vertical axis, the y-axis, measures the braking force in increments of 200 pounds. Right, so 200, 400, 600, 800. The distance across the bottom measures the separation between the magnet, the stator, and the strike plate in hundredths of an inch. So, wow, that's fairly small, right? Can we do something to maybe break that up? So we could put something between the strike plate and the magnet. That would make the lock easier to open, right? Depending upon the thickness. If we find something that's, let's pick a number. Let's 4/100ths of an inch. We're right here, and it looks like that takes us down to about 100 pounds of force to apply to the door. It's very doable, very easily doable. My kids could get in there and would be terrible. But my kids could open that up. So can we do that? Can we just put something there and then later on we can come back and open the door and walk in like we own the place? Well, maybe. But this can be detected. Right? These locks, as I said before, they can use a small current that goes through the strike plate to make sure the door remains closed, making sure it's truly closed. And so we might notice that the door is open, and then we notice it never fully closes. And after a period of time, the door being open, maybe you get an alarm, and that's a bad thing. So we don't like that. So maybe there's something else that we can do. Is there some way to overcome this? Can we figure out some complex, sophisticated way of overcoming this current detection magnetic lock thing? Well, we could buy some tape. So what you're seeing here is EMI shielding tape. Tear apart anything electrical, and you'll probably find this metal tape that's on certain items. And that metal tape exists to absorb EMI, electromagnetic interference, electromagnetic radiation. So anything that generates a current in your computer, in your phone, wherever, it generates a field. That field causes electrons to wiggle around, and we don't want electrons up here wiggling around. We want the electrons to be wiggling around where we want them, and we don't want the field to be moving them around elsewhere. So you put this metal tape on things. In this case, it's aluminum tape, and the electrons in the tape wiggle, and the field doesn't go out and cause other harm. That's all the physics for today. And so here's some conductive electrical tape. If we put this on the surface of the lock or the strike plate, it adds some material there. It's conductive, so you won't necessarily notice that the door, the door will appear to be closed, and there we go. Well, it's 20 mil tape. How big is 20 mil? Well, a mil, it turns out, is a thousandth of an inch. So this is 20 thousandths of an inch, which is 2/100ths of an inch. So it's 0.02 inches, and that's on our scale. If you remember, that actually puts us right about here. And you can see that we end up just under 300 pounds of normal force on the door to open it if there's a single layer of that tape on the door. So a friend of yours who works there, or you, as you're walking out, you just sort of casually slap the the little door thing, and you put a spot of that tape up there. And when the door closes, it only closes to within 2/100ths of an inch. And then later on, some other opportune time, you come back and you walk confidently up to the door and you swipe your library card or your whatever you have in your pocket, and confidently swipe that, and then you take the door and you give it a good, strong, hard yank. And 300 pounds, you absolutely can apply that much normal force to the door and a good yank. You're not trying to lift weight above your head. You're just trying to give it a good, solid, strong yank, and 300 pounds is well within your abilities. The door opens, and you walk in like you own the place, and people saw you walk up and badge and open the door and walk in. Life's good. Still, it's 300 pounds. I mean, I could use 2 layers of tape, I guess. 2 layers of tape would drop us down to under 100 pounds. So what's the point of all this? Well, the point of this is that security depends on a bunch of things. And we're going to talk a lot about what makes something more or less secure, and how that may change over time, and really what that means. But we can learn a few things from this. Security depends on your environment. If there's no one around, just force the door open with a Halligan bar. Easy and simple, you're good to go. If it's the middle of the day, you probably don't want to do that. Security can be overcome by cooperation. An insider can place tape on the strike plate pretty easily. It's a gray tape, no one's going to notice it, and that can allow others to defeat the lock at a later time. And adversarial capabilities, right? How hard is it to overcome such a system? Do I need specialized knowledge? Do I need special resources? Does it take a lot of money? Right? Well, it turns out it doesn't take a lot of money for this. I don't need super specialized resources. I do need some knowledge, though. It's helpful for me to know something about the lock itself. And so maybe I can stand at the door. These doors are usually glass. And look in, and maybe I can see the writing on the lock. Write that down. I then go look it up and find out what I can find out about it. Right? This is a case where an adversary is able to get knowledge about a system, and that tends to be bad. You don't want the adversary to get lots of knowledge. In fact, in some cases, people put little stickers over the model numbers for these so that you can't see that. You don't know. We'll talk about some good examples of that later in the class. My point is that here we have a system clearly designed to provide security, and in combination with other things, the door itself, card readers, and systems that support all of that, we can ask the question, is this a secure lock? Well, I would argue that it's neither secure nor is it insecure. I would argue that it depends on the context, the entire system around it. And the system that includes a magnetic lock can be more or less secure, depending. Security occurs at interfaces, places where 2 components or 2 systems interact, where a human interacts with the door, where a human interacts with the card reader, where a card interacts with the card reader, where the card reader interacts with the lock, where some computer system somewhere interacts with the card reader in order to enable it. Go on and on and on. Lots of interfaces in the system, even to the point of where the stator and the strike plate interact. Those are all places where I can look for opportunities to subvert the security of the system. Okay? Security issues often arise because of a failure to consider all inputs. Very common in software, and we'll see that next time. Security issues arise when information is given to an adversary. We'll see a really good example of that as well. And we have to consider all of these things. And finally, we give access to people. And those people can turn around and give that access to others who shouldn't have it. And they can do that intentionally, or they can even do it unintentionally, right? I mean, they can do simple things like clicking on a link they shouldn't click on, or giving information to someone on the phone who calls and asks a question. And we'll talk a little bit about that some as well. We're going to talk a lot about security because in order to understand whether or not a thing is secure and how you would know if it's secure, you kind of have to know what security is. All right, let's talk about the class a bit. So the basics, I'm Stacy Prowell. I am a security researcher at Oak Ridge National Laboratory. Prior to that, I was a security researcher at CERT. I've been a professor at Carnegie Mellon. I've been a professor at UT. I've been a professor. I think I'm a professor at Georgetown right now, although that's weird. And I'm a professor at Tennessee Tech. I split my time between Tech and Oak Ridge. And so on Tuesdays and Thursdays, you can often find me at Tennessee Tech. I do have an office here. Prescott 409 will be my office. You see the RSN next to it, and if you're familiar with your internet acronyms, you'll know that that means not really. Theoretically, at some point, I'll be available in that office, but for right now, if you want to get a hold of me, the best thing to do is to reach out and set up a time to meet with me. Appointment sounds really formal. Just find a time. Just tell me you want to meet, and we'll meet. My email is there. That's probably the best way to get me. I try to be consistent at reading my email during the school year. If I'm not responding and you really want to get a hold of me, call or text me at that number. Texting me is probably more reliable because I get a lot of spam calls, a lot of junk calls, and I might ignore yours, or T-Mobile might label yours as spam. So texting is probably a little bit better. But that's my cell number. Really, feel free to reach out to me on that number. It's perfectly fine. It will not bother me a bit. It'll bother me if you don't, because you need to be able to reach out to me. There's no TA for this class. We are on our own. The class meets on Tuesday and Thursday. If you're in Cookeville, and I think most people are in Cookeville, we meet at noon. If you're in Oak Ridge, through the magic of time zones, you get an extra hour. We meet at 1 p.m. We're going to meet in Bruner Hall. I'm going to try to put the class online via Zoom. I'm going to try to record them and make them available later. As you can tell by the fact that I'm not in Bruner, the last recording for some reason consisted of bad audio, and that picture from those of you who were there earlier will remember the picture from the camera on the wall that was pointed at nothing. We managed to capture that, but nothing of any value. So that was this re-recording, and I'll put those on iLearn. So there's the Zoom information, the Zoom meeting number, and the password. You may look up what Stephen P. Morse did in 1976 if you're curious. Online information is important. There will be a time when I will have to cancel class or switch to doing it remotely with very little notice because of work. It happens every time I teach a class there. It'll be the night before, it'll be late, and I will send out a note saying, I've got to cancel class, or I've got to do it remotely, I'll record a video, something like that. And I hate to do this to you all, but it's just what happens. It happens at least once a semester. And I will do what I can to prevent that, but it's going to happen. And so the online information is important. Plus there's COVID. And who knows what's going to happen with COVID. I don't know. For this class, I'll try to make the slides available right before the class starts. Classes will be recorded and eventually made available through iLearn. Hopefully I can turn this around a little faster. We'll see. There are 2 exams. There's a midterm and a final, and that's it. The midterm counts 20%, the final counts 20% for a grand total of 40% of your grade. There's homework every Tuesday. It's due on the following Tuesday. So this is not Tuesday. No homework today. You managed to sneak by. The homework counts 60% of your grade. So the majority of your grade is homework. Homework grading, pretty simple. You got it right, you got it wrong, or you're somewhere in between, and I'm willing to give you some partial credit for it. And that can include being late. So turn the stuff in. If you're late, you should still turn it in and get a point. I'll drop your 2 lowest homework grades. So if you just absolutely skip out on the homework once or twice, you're still okay. Homework is cumulative. New assignments will build on old ones, so please don't get behind. And please try to follow the instructions, because I would love to be able to automate the grading of the homework, because there are a lot more students in this class than I thought there would be. So please try to follow the instructions. Exam grading, it's pretty simple. Exams are graded out of 100%. Both exams will typically consist of a number of questions, say 15, where only the best 10 answers are counted. I tend to write hard questions, so it's better to give you more hard questions. Both exams will be take home. You'll have about a week to do them. The material is cumulative, so the exams are cumulative, and the exams focus on principles. This is the university calendar. It's got lots of stuff on it, but all we really care about for this class is this. You can ignore the first line. It's already happened. Midterm comes out at the end of September, right before the fall break. I don't want you to have to do anything on the fall break for this class, so the midterm's due before the fall break. Thanksgiving is the only holiday we get off from this class. It's the only one that happens to align with one of the classes. Last day of classes is the 1st of December, when the final exam is handed out, and it's due not quite a week later at the end of the class's exam period. If you have a documented disability and you would like to talk to me about that, please do. I want you to learn. Everyone here wants you to have a good learning environment where you can get the maximum out of the class. And if there's something that we can do to support you to achieve that, just let us know. If you don't want to notify the university and document your disability, but you'd still like me to know about it, feel free to tell me. We can discuss it. That's fine. Happy to help in any way we can. We're all here. Hopefully we're all here to learn this stuff, and so let's work together to do that. I expect you to take responsibility for your own work and give credit to others for their work, share credit for collaborative work, to treat others the way you would want to be treated, and to deal honestly with everyone around you, including yourself. Value your own intellect. You're in graduate school at a university, okay? You're surrounded by people who have been through this and are going through this, and everyone's here to help and support you, okay? Universities exist to teach people stuff and take money from rich donors, okay? We're here to help. Let us know how we can help. Don't do something that you would regret. Don't cheat. Don't turn in someone else's work as your own, etc. I'm not going to tolerate that. The university is not going to tolerate that. It's not going to be good. And there's no reason for you to do that. If there's some kind of a serious problem, let me know. All right. Expectations for the class. I expect you to come to class, to read the reading material. I expect you to do the homework, and I expect you to email me with questions, and I expect you to text me if I'm ignoring you or not responding, okay? I expect you to know a reasonable amount of C. I'll show you what that is in a minute, what I consider to be a reasonable amount of C. Maybe some C++. We might do some Linux interaction. I expect you to know some basic discrete math, the kind of discrete math that you would have picked up from your computer science education. An example of something you should be able to read, even if you don't quite understand it, is at the bottom, where it says for all x and y that are in the domain of f, whatever f is, a relation, a function, who knows. I want the ordered pair xy to be in something called k of f if and only if f of x is equal to f of y. So if f of x is equal to f of y, then that pair needs to be in this little thing called k of f. It's the kernel of a function. Here's what I consider to be a reasonable amount of C. Everything in here ought to look pretty normal and simple to you. By now you ought to know how to use the standard integer types provided by the C language. That's uint32_t and uint64_t, etc. You ought to know how to print with them. There are little print things that have been defined. Those insert the correct stuff in order to print an unsigned 32-bit thing. The only thing that might be weird to you that you may not have seen before is right here in this line where it says I'm going to declare, in this case, an array of function pointers. A function pointer in C is pretty easy. You write the function prototype, just like we did with main up here at the top. You write it just like that. You put main, the name of the function, in parentheses. You put an asterisk in front of it. And if you want an array of them, you put, square brackets after it. And that's just what we did down here, and that's how you declare a function pointer, in this case, an array of function pointers. And we stick some functions in there. So there you go. Shouldn't be anything too complicated. That's about as complicated as we can expect it to ever get. This is a 6,000 level computer science course, and so I expect you to know how to read and write programs. This should not be the first time you've encountered a computer. If it is, you're in trouble. I expect you to be willing to learn some things, learn some security theory. This is an upper division class. If this were an undergraduate class, I would just tell you what I think security is and how to deal with it, and here's some tools to use. But it's a 6,000 level course, so I'm going to expect you to help me figure out what security is, to try to understand what that might mean. And yeah, sure, you'll learn some maybe new to you programming tools, but also will want to learn some applied computing theory. All right, so be prepared for that. I expect you to run experiments and try things and test things out and play with stuff. They're computers, right? They're supposed to be fun. Turn it on, load some stuff up, play with it. If you can get the answer to a question by running a tool or writing some code, then go do that, okay? There you go. That's the answer. Learning goals. You should learn what makes a program an insecure program. What is an insecure program? What's a weakness, a vulnerability, and an exploit? What's a secure program? How can you write a secure program? How would you know if you wrote a secure program? And I expect you to know why none of those questions have easy answers, because none of those questions have easy answers. So your learning goal is understanding how to think about security and insecurity of programs that you write or you review. I like to think of this as, I want you to come out of this class with a security mindset. And that means I'm going to throw a lot of things at you. Stuff like the magnetic door lock up front. I want you to think about systems, how they work, how they interoperate, and how they can be defeated. Okay? Come at things with security mindset. So there's going to be a lot of that. Just get ready for it. So you've probably been told computers do exactly what you tell them to do, and that's why it's hard to program computers, because you've got to account for all the little behaviors. That's a great story, but it's not true. Computers are complicated little monsters. No matter how complicated you think a computer is, you're wrong. It's more complicated than that. Computers do a lot of stuff that is non-obvious. They will do work you didn't ask them to do. They will not do work you did ask them to do. They'll reorder the work schedule based on stuff you couldn't anticipate. They will just behave in their own little way. So here's an example of some code. Promised you C code. Here's some pretty simple C code. Little function taken from a program that I won't name, which aims to unlock a resource. So there's a security vulnerability in this. Pause the video and see if you can spot it. Okay, we're back. Did you spot it? Well, if you were looking really closely, you might have. It's right here. So up at the top, we get a password, and the value comes back to us as a char star. Okay, so we get back some result that's a sequence of chars. We check to see if it's the null. If it is, then we return 0. We don't return a null. We return a 0 because the result is a 64-bit integer, not a pointer. So really, this was a pointer, so this is a null. This is an integer. This is just a long integer. We declare another 64-bit thing called hash. And then we try to acquire a lock using that password and passing in a pointer to hash. The idea being that this will fill the hash in for us if the password is correct. And we get back a return value. If the return value is non-zero, we return 0. Okay, right here we're saying, well, if I couldn't acquire the lock given the password, then I'm just going to return 0. Same thing as if I couldn't get the password up here at all. Then I get the length of the password, save it in len, and I have a little for loop here. And I loop from 0 up to the length of the password, and I overwrite each entry with FF and then with 0. So I erase the password. This is kind of aggressive. I think overwriting it with 0 is sufficient, but okay, fine. So I overwrite the password in memory, and then I free the password and return the hash. So you may see the problem here. Up here, when I try to acquire the lock, if it fails, I return immediately and I leave the password in memory. I don't do this loop to override it, which means if somebody can look at my memory later on, they may be able to extract the password and see what it was. In fact, they may be able to engineer things so that acquire lock fails even if the password is correct. In which case, the password is left in memory and they can go look at it. And even if they can't do that, a bad password is probably a very good clue to a good password. Right? If they see that you typed password 123, they will think, password, maybe that's password, and they just typed it too fast. Let's try that. So that can give your adversary some information, and you don't want to do that. In addition, there's a memory leak. Up here, we call get password, and we get back a char star. And then down here, we free that. So if we couldn't acquire the lock, we return 0, and we never free the password. We don't override it, and we also don't free it. That's great because that helps me find your password in memory. It's going to be in a piece of memory that has been allocated long term, and it means that I can maybe have my code that looks at the password run long after this stuff happens. And it's not going to go away. It's not going to get overwritten because that memory never gets deallocated. I don't have to worry about that. Even more helpful. And with something that's checking for a password, a memory leak like this is going to persist for a long time, and you're not going to find it, right? It's not in a big loop where you're consuming tons of memory every time. You're consuming little chunks of memory. Each time you have to go and do this unlock operation. All right. So perhaps I can trick the system, and then I can get the password. It won't get overwritten because it's never free. So how do we fix this? What do we do to make this all better? Well, one thing I might do is move that check down. There's no reason not to, right? Here what we do is we overwrite the password and then we free it. Fine, because either we've already acquired the lock hash, which we're going to return, or we haven't. And so we go ahead and overwrite the password and free it, and then we check the return value and return 0. Aha! This is much more secure because the password gets overwritten and the memory leak is gone. So clearly this is secure code, right? Of course. So the next thing to do is to compile it. So we'll compile the code. Now, I know not everybody has been through the travails of looking at assembly, but bear with me and I'll walk you through this code. So this first instruction, NBR64, you can ignore. Think of it as a no-op. We push the base pointer on the stack, and we push RBX on the stack because we're going to use it, and by the calling convention, we're required to save it. You'll see down here at the bottom, we pop them off the stack in the reverse order because that's how a stack works. We then do a subtraction. We subtract hex 18 from RSP. So we reserve space for 24 bytes, right? 16 plus 8, 24 bytes on the stack. And what are we going to do with that space? Well, one thing we're going to do with it is we're going to go get a value out of our thread local store, and we're going to put it in a register RAX, and then we're going to put that contents of RAX over into the stack at offset 8. So we're storing something, in this case a 64-bit integer value on the stack. We zero out EAX, and then we call get password. So what comes back to us in RAX. And so we check to see if the return value was 0. That's what this test does. And if it is 0, well, then we follow this line all the way down to here, and we'll talk about that later. So this is our get password. If the return value is 0, go down here. Assuming the return value is not 0, then we do some things right here. In particular, we take the password we just got, the char star, and we put it in our DI, which is by the calling convention where the first argument to a function goes. We put RSP in RSI. RSI is by convention where the second argument goes, but wait, you're probably saying, why RSP? Remember, we reserved space up here at the top. We used some of that space, used 8 bytes at offset 8 to store something, but that left the first 8 bytes at RSP free, and we're going to use those now. So we put a location, a pointer here in RSI. If you remember our code, the first thing was the password, the second thing was the address of hash. So local variables are typically put on the stack, and that's where this is. We then take RAX and also put it in RBP. Why are we doing that? Well, RAX holds our password. We're going to need it again later, and so we temporarily stash the pointer to it in RBP. we need to do that because when we call acquire lock, it's going to overwrite RAX with the return value. Assembly language is hard. So we call acquire lock, and then we take RBP and put it back into RDI. So if you're following the tail of our password, it's making its way around. It went from RX to RBP, and then from RBP to RDI, which we know is where you put the first argument to things. Okay, we move EAX into EBX. What is EAX? Return, right? That's the return value that came back from acquire lock. What about the hash? Well, that went straight up into the stack because we passed it a pointer up into the stack. All right, so return value goes in EBX, so it's temporarily being stored here. We have to do that because we're about to call free, and free will overwrite EAX with its return value. It's the way the world is. So we call free. What are we freeing? Well, we're freeing whatever's in RDI, first argument by convention, which happens to be RBP, which happened to be RAX, which was the password. Okay, so we're freeing the password. We then check to see if EBX is 0. What is that? That is the return value from acquire lock. So if that's 0, then great. If it's not 0, then it's a problem, right? It's the opposite thing up here. So instead of doing jump if equal, we do jump if not equal and come down here. So now we're still on the good case, okay? And what we do is we go and get the value pointed to by RSP, grab the Q word or the 8-byte 64-bit word and put it in RAX, which is the return value for the function. And then we jump down to 1202. Jump down here. There's a no op here. That's for alignment. Causes those to be 0. Ignore it. All right, so a couple different things are going on here. If we fail here or we fail here, we jump down here and we set EAX to 0. Otherwise, we jump down here and we skip that because EAX has been set to the hash value. So it's going to be the return value, so it's 0 on error. It's the hash value when things are right. We then go ahead and take the value at RSP plus 8. Remember, that's where we stored that thing from thread local storage, and we compare it to that thing at thread local storage. It should be the same. Nothing should have messed with this. And if they are not equal, well, something messed with the stack. And we jump down here and we call stack check fail. Otherwise, we go ahead and add hex 18 back to the stack pointer, the opposite of the subtraction up here. So if we return that space to the stack, we pop RBX and RBP, and we return, and the return value is an EAX. Okay, it's a lot to think about. One thing to notice is we didn't ask for this stack stuff up here and here. We didn't ask for that. The compiler added that to protect us against stack smashing attacks. It's a stack canary. Another interesting thing to notice is that the loop that overwrites the password is gone. It's not there. There's no loop. At no point are we overwriting something with FF or with 00. It's just not happening. The compiler did something called live variable analysis, and it determined that password was quote-unquote dead at a certain point in the program. In other words, nothing else was ever going to read its value and pass that information outside the function. So its value didn't matter, and the compiler marked it as what compiler writers call dead store. And the compiler is free to discard anything that happens to dead store, like our loop. Gone. So that's a problem. We went through all that effort and work to be sure that that loop got run to erase the password, and the compiler threw it away. This is very common. How do you deal with it? You can deal with it by adding an attribute that says, do not optimize my function. That'll work. That has the advantage that it's easy. The disadvantage that your function doesn't get optimized, which can be bad. So we can target it more directly at what we want, like this. Here we've used a pragma to turn optimization off and then turn it back on after that loop. So the loop is then preserved using this method, and the loop doesn't get optimized, but everything else can theoretically be optimized. In reality, not optimizing the loop means that storage to do with index and so forth can't be optimized, and so it can bleed over into the rest of the function, but it's better. Still, maybe the best way to deal with this is to declare password to be volatile. Volatile is a keyword in the C language, which means this variable can be modified outside the scope of the current function or loop or whatever. So you, compiler, you can't assume things like it's dead storage, because you don't know who is using this outside the scope of this function. Okay, there may be a parallel thread that's referring to what's in password, and so you have to go ahead and include this loop. Now you may wonder why there are all these casts of password, which is a char star, to char star. That's done to remove the volatile modifier, because acquire lock doesn't expect to get anything volatile. Sterling does not expect to get anything volatile, right? If Sterling took a volatile argument, it would not be able to work, because it wouldn't know, can I count these characters? Is somebody modifying the string off to the side? Well, in which case, I don't know how to count the characters in it. Same thing for free. If it's being modified, I don't want to call free on something while it's being modified. And so, since I know that in reality, password's only used in this function, it's safe for me to go ahead and do this cast that removes volatile and allows me to pass it to these other functions. The point of all this is compilers are free to discard work, throw the loop away, add to it. It added a bunch of stack stuff I didn't ask for, and to reorder the work. And if you look back at that code, you'll see that some things are sort of moved around in a way, like returning 0 or setting the return value to 0, that makes sense to the compiler. They're free to do all this stuff. In fact, it turns out assemblers can do this as well. Assemblers do much less harm, but they have optimization settings. So for example, on the x86, an instruction like this, you might write this instruction, and then when you assemble, you might then see that it's substituted it with this instruction. You said move hex 21 into the register RAX, a 64-bit register, and the assembler said, okay, I'll move hex 21 into a 32-bit register EAX, and because it knows about automatic 64-bit extension. There are ways to overcome this too if you need to, and sometimes you need to. Sometimes this is the wrong answer. Okay. The processor is free to reorder the work, discard it, and add to it. It really is. Processors do out of order execution. And in addition, they can throw work away, and they can do work you didn't ask for. In fact, your processor is constantly doing work you didn't ask for. It's called speculative execution. So the compiler and the processor can do work out of order, can do different but equivalent work, can do extra work, and can just not do work you told them to do. As long as the overall effect is the same, the compiler and processor are free to do anything. sometimes the overall effect is not the same, and that's kind of the point. Whenever these things change the work schedule, you have the potential for a side channel vulnerability, and modern compilers and processors always change the work schedule. So there's plenty of opportunity for that. Does this mean all hope is lost? No. There's a lot that you can do to make sure that your program is, to make sure that your program doesn't fall into any of the obvious dumb traps, and maybe even to make sure that your program can make some guarantees about what it's doing in terms of providing some security. So, some questions to think about. What does it mean to write a secure program? Is it even possible? Right? I've spent a few minutes trying to convince you that it may not even be possible. Is it possible? And how would you know if you had done it? It's not Tuesday, so there's no homework. So you're in luck. And that's it. I'll talk to you next time.